For all the families of functions we've been working with, we have taken a look at how we can create an inverse of it. And when we looked at inverses, we sometimes had to restrict what domain we had because the original function didn't allow you to flip the x and the y in order to get an inverse unless you restricted that original domain. That's going to be the case with trig functions. So our objective here is to be able to use the inverse trig functions, but we first of all have to develop what is an inverse trig function. So let's look at, going backwards, talking about inverses. Let's look at a parabola as an example. We use two types of tests to be able to determine whether an original graph was a function and then whether the inverse of that graph would be a function. The vertical line test helped us to determine, is it a function? So the question for the vertical line test is it a function? Is the question we use for that. And if you can draw a vertical line and only hit it once, every time, any vertical line you draw, notice that it passes if it does not hit the graph more than once. So any vertical line I draw here, I would only hit the graph once. So since this passes, it is a function. So y equals x squared is a function. And so what we define that is, for a function is, for every x, there is one y, only one y. So that x value right there, that's the only y that goes with it. If it hit it more than once, there'd be two y's, so it would not be a function. So now we use the horizontal line test to see if we flip the x and the y in the formula, would that be a function? And in this case, it wouldn't, because if you notice, if we draw a horizontal line, it hits it twice, it doesn't pass the test, it hits it more than once. So the inverse, the question we're asking, is the inverse a function? And the answer here would be no, it is not, the inverse is not a function. Okay, so if that's the case, if we can take it, what we want to do is be able to restrict it. And if we can restrict the domain here so that it can only hit it once, then we would have the inverse being a function. So in that case, what we want to do is we want to take and look at this graph. And if you look at this graph, and if I start at 0 and go from there and restrict it to just x is greater than or equal to 0, then I've got a one-to-one function. Okay, so it is the restricted function is one-to-one. So what we say by that is not only is for every x there is only one y, but also for every y there's only one x. So we want to do that for this graph. Let's take a look at what this function would be if we restricted it to do that. So if we take these ordered pairs and flip them, so 0, 0 flipped would be 0, 0. Then if I take this point here, so 1, 1, flip it, I still get 1, 1. But then if I go up here and take this point here, which is 2, 4, it becomes 4, 2. When I flip the x and the y, this is the graph of the inverse with the restrictions, which is the graph of y equals the square root of x. That's the inverse function as defined with that restricted domain of the original in order to give me that new flipped x and y, the inverse, the square root of x is a function. All right, so let's do that now with trig equations. If you look at these, our trig, different trig graphs here, they don't pass the horizontal line test. They pass the vertical. They do qualify as functions, but when I draw a horizontal line, notice it could hit it multiple times. In fact, if you think about a sine graph, it goes on this sine wave forever in both directions. So this horizontal line would hit an infinite number of points. So we have a lot of restricting to do to get it down to where it has only 1 point. So let's look at 0 here, just to be specifically with this one. Notice that here's 0, when I put it in, 0, 0, 0 for what I'm putting in. What angles am I getting out for that value? And I get all these different angles. So let's restrict it so you only get 1. So let's take a look at this graph now. And if I restrict it from here to here, notice this portion of the graph, it only hits the, that horizontal line once, and every horizontal line. Now with that restriction, I now have a one-to-one function. And so the inverse of sine of 0 would be 0. I'd get out that other value. So if you look at this, this is from negative pi over 2 to pi over 2 if you're dealing with radians. If you're dealing in degrees, that's negative 90 degrees to 90 degrees for that. Let's do the same thing with cosine. Let's restrict it. Now you might say, why don't you just restrict it to the same thing? If you restrict it from negative pi over 2 to pi over 2, if I extended this back down to negative pi over 2 to make it one-to-one, notice it wouldn't. This part of the function, that is not, does not pass the horizontal line test. So we can't use the same restrictions for every trig function because they move. This one is translated over from the sine function. So instead for this one, if we just start at 0 and go to pi, notice this portion of the graph does pass the horizontal line test. So if we go from 0 to pi, or at 0 degrees to 180 degrees, we now have a one-to-one portion of the cosine graph for my inverse. Let's look at tangent. We keep having these tangent parts whenever we do a new period. It doesn't pass the horizontal line test, but it does pass the vertical. It's a function, but not one-to-one. So how do we restrict this one? This one we can also go from negative pi over 2 to pi over 2. Okay, but we don't want to include this because there's an asymptote there. But negative pi over 2 to pi over 2. Or if you do it in degrees, that's going to be negative 90 degrees to 90 degrees for this part of the graph. All right, so let's use those restrictions and talk about inverse trig functions. Here's the notation. We've started alluding to it. What this means is this little negative 1 here, when you have that in the front there, and the top there, that means the inverse function. The inverse function, it goes with this idea. Notice, remember when we've done with that little negative 1 before with f of x, that meant the inverse function. This is the inverse of f of x, the inverse function of it. So that's the notation we use, and it only has, it's a function, so only one answer for it. We don't get into the multiple answers. We'll do that later when we solve trig equations and build on that. But for this, you're only going to get one answer when we use this notation. And something you have to recognize is you're putting in the x value, you're putting in what's been flipped. It's the value you get out from the original trig function. That means that this here, the answer you get out is an angle. The answer for an inverse trig function is the angle. That's an important one, okay? So the answer for an inverse trig function is the angle. That's an important idea to get when you're dealing with these inverse trig functions. You're getting out an angle as a result. So let's summarize now with a table for this. This is going to summarize our what our domain and range is, and also what the inverse graph looks like for each of these three: sine, cosine, and tangent. So inverse sine, the notation we use is inverse sine of x with that little -1. Same with the cosine, and then same with the tangent. Now we want to deal with the domain. Remember that the range is going to be the angles. That's what comes out of the inverse trig function. The domain are the values that were the outputs originally for the trig functions. So the domain, if you look back at this graph for each of these, okay, let's actually highlight this here. The domain here is going to be what the y's were here, because we flipped the x's and the y's. So the domain will go from -1 to 1. It actually includes those because it has actual points at -1 and 1. All right, so for the sine, notice that the range, the y values here, the y values go from -pi/2 to pi/2 if we're dealing with radians. So -pi/2 to pi/2. Or if we're dealing in degrees, it goes from -90 degrees to 90 degrees in degrees. So if we're dealing with the cosine, it has still the same, the domain is the range of this one. So it still goes from -1 to 1. So the range of the original is the domain of my inverse. So from -1 to 1 for this one, same domain as this one. But the range changes. Notice that these x values become the y values of the inverse, and so these x values from 0 to pi are different than the inverse sine. And if we use it in degrees, it's 0 degrees to 180. All right, and lastly for tangent, notice that on tangent, the y values here become the x values on the inverse. So the y values here go from -infinity to infinity. So the x values go from -infinity to infinity for the domain. But now the range, the y values here are the original x values in the original problem. Notice I never get to -pi/2 or pi/2. So when I list this one, I'm going to list it with a parentheses to say I never actually get to that one for my open and close notation. Or if I do it in degrees, I never get to -90 degrees or 90 degrees because there's an asymptote there on the original x. Now flipping these over when it comes to the points, notice I'm going to take this point here. When I look at my domain, notice my domain goes from -1 to 1. And then my range values are going to go from these values. I'm going to keep this one. I'm going to go ahead and list it here. Here's my pi/2 or my 90 degrees. And down here, I'll put -pi/2 or -90 degrees for my range values. Now, these points, notice that this point here is -pi/2, -1. So we're going to go with -1, -pi/2. So we're going to flip them. It'll be down here. 0, 0, we'll just flip the x and the y, get 0, 0. And this one is pi/2, 1. I'm going to flip it and make it 1, pi/2 for this one. Okay, so there's my graph. And then the curve of it looks like this. It curves in like this, and then curves out like that. All right, so that's the graph of my inverse sine function. Now, the inverse cosine function, again, I'm going to go from -1 to 1. Now I'm going to go from 0, I'm going to focus on these, but you go from 0 degrees here up to it'll either be pi or 180 degrees. On this graph, I'm going to focus on the degrees. I did this one in radians, let's do this one in degrees. So this one starts at 0, 1, so let's graph 1, 0. Notice there's 1, 0. And then I'm going to go with, this is at pi over, this one, this graph here is at 90 degrees right here. So 90 degrees, 0. So let's go ahead and when we graph this one, we're going to go with 0, 90 degrees, so right in the middle here. And then lastly, we're going to go with this point here is 180 degrees, -1. We're going to go with -1, 180 degrees for the inverse. And then its graph will go in like this and out like that for my inverse graph. And lastly, we'll do tangent. Okay, so tangent you're going to have down here, because it goes off to infinity in both directions for the x. I'm going to have down here -90 degrees, or -pi/2. And up here I'll have 90 degrees, or +pi/2. And then it just looks like my tangent going sideways from here, going that direction for my inverse tangent. So it never gets to the -90 or the 90 degrees. So that's what my graphs look like, and a summary of the domain and range of each of those. Now let's practically look at a unit circle and how that works with these problems. So remember, when we do the inverse function, that means you're going to flip the x and the y. Okay, so you flip these two. Now you're going to solve for y, and that means you're going to do this inverse trig function. So this is my inverse. So when I'm asking for the inverse of 1/2, you go to a chart like this and you say sine is the second value. So here's a 1/2. Here also, over on this side over here, this is a 1/2 also. Well, which one am I going to take? I got two different 1/2s. I got -1/2s down here, so I'm not going to use those. Which one do I take? Do I take the 30 degrees or do I take the 150? Well, looking back at these here, it's between 30 degrees is between -90 and 90. 150 is not. So I'm just going to take the 30 degrees. I'm going to take the one in the first quadrant. So if you think of it this way, the range here, this is in the second, the first quadrant and the fourth quadrant for this. So I'm going to take this one and I'm going to just take and make it 30 degrees for that. Cosine, on the other hand, it has between the first quadrant and the second quadrant from 0 to 180. So when I look at this, I look at -square root of 2 over 2 for my x value. So here's -square root of 2 over 2 for the x value. Here's another one that has -square root of 2 over 2 for the x value. Which one do I take? Well, I take it in the first or second quadrant between 0 and 180. So I'm going to take this 135 degrees. So you've got to get used to where you're looking on your table as to which value you're going to take. So what we've done is we've developed the inverse trig functions by looking at how we did inverse functions with our other families of functions, specifically with parabolas with an x squared. And then we looked at how we can restrict sine, cosine, and tangent to pass the horizontal line test, restrict the domain of the original function so it becomes 1-to-1, and then we have the inverse being a function where it passes the vertical line test. And then how we know that now the new notation and how we can use that notation to find values of these inverse functions.